Okay, so good afternoon. Welcome back to the weekly live tutorial sessions and discussions on ME92, Mechanics and Control of Robotic Manipulators. I am Isaac John, and I'll be the TA who will be handling over the weekly sessions. So I hope the progress for the course during this period of 5 weeks have been satisfactory so far, right? Okay, so yeah, and just to give a brief overview of this week's topic, we will be covering for the duration of this session, we'll be covering the topics including equations of motion in state space form, dynamic models using Euler-Lagrange and Newton-Euler methods, and dynamic simulation of serial manipulators in MATLAB. So the simulations in MATLAB have already been covered during the lectures by Professor Shantakumar. We have also covered the topic on trajectory generation. That was also covered that was also simulated in MATLAB, which will be carried over for the next week's sessions when we get onto the robot motion controllers. So basically this week, the topics that we will be covering uh, to to derive the equations of motion of a serial robotic manipulator, right? So in essence, we would deal with dynamics of robotic manipulators. So until now, we have been dealing with kinematics and statics, where we would not take forces, or what we were only dealing about motion without considering what actually causes the motion. So now we would be proceeding on to the topic of dynamics, where the interrelationship between motion and the effects that causes this motion will also be considered. So until now, we have actually discussed conventions, maybe this DH conventions and all those things, and then how to define this, this DH parameter convention for the robot kinematics. We have also seen a few examples regarding the same. So now that we have done enough examples using DH parameters, now we move on to more involved topics, which is robot dynamics. So moving on, so just as what we did in the previous session, for the first part of the session, we will give a brief overview of the topics that we have discussed for the duration of week 5. Then for the later part of the session, we would do some sample questions, that is more or less similar to sample questions that is more or less similar to what you can expect for your weekly quizzes. So moving on, for robodynamics, dynamics in general is nothing but a study of systems that undergo changes of state as time evolves. So it's not something that restricted to robot manipulators. So any system, any physical system can have dynamics, which basically is a study of its change of state as time evolves. So in mechanical systems such as robot manipulators, the change of state involves motions. So like in case of a robotic manipulator, its state is basically defined by its configuration, a configuration defined by its joint variables. So if the state changes as the time evolves, the study of all the states that is involved, maybe positions, velocities, forces, that is what we cover for robot manipulator dynamics. So the motion can be considered as evolution of position and orientation, as well as their time derivatives, which are nothing but velocities and accelerations. So in robotics, the dynamic equations of motion for manipulators is utilized to set up the fundamental equations for control. So what we basically now, through the procedure or through the methodology that we have covered for this week, we would be defining the governing equations of any serial robotic manipulator that is necessary for controlling. Or if you want to design a control system, for a specific serial robotic manipulator, what should be the governing equations of that robot and how do we derive that? All these topics we will be covering in robot dynamics. So robot dynamics, the way in which the motion of a robotic system arises from torques or forces applied by the actuators or from from the external forces and moments applied to the system. So basically, the equations of motion or the dynamic equations of motion of a robotic manipulator tries to find a way to correlate the forces and torques that the robot is subjected to, be it from be it external forces and moments, or it could be the forces and torques that is applied by the actuators and the resulting motion due to this effects. So, as an example, if you consider a 2-hour serial robot like this, comprising of 2 links and connected by 2 revolute joints, should be familiar that the axis of these revolute joints are parallel as well as they are also out of plane. So if this is a robotic manipulator subjected to forces at the center effector, for example, if the task of the robotic manipulator is to pick a load from a position and place it on another position, uh, because of the physical weight of the payload or the physical nature of the payload, the end effector would be subjected to forces Fx, Fi, Fz, as well as the moments Mx, My, Mz. So what I have considered is a generalized case. So in case of a planar manipulator like a 2-hour robot, you would need not consider all the 6 variables. You only need to consider the planar coordinates, probably Fx, Fi, and Mz. So just to give a general idea, the forces involved for a robot are the forces that is acting on the payload, external loads. There could be external loads on the links, that could also be considered. Then what are the other loads? The loads that are acting on the actuators, tau1 and tau2. So you could consider this as the inputs or the torques that you supply onto the motors. So if these are the forces and torques involved, and the motion of the robot can be characterized by the joint variables theta1 and theta2, that is in the joint space coordinates, or you could consider the motion of the robot in task space coordinates x and y. Either ways, it's fine. So the F, you can consider it in both ways. If these are the forces that are acting on the robot manipulators, then what should be the corresponding inputs that you should be giving onto the motors, right? So addressing if you address this question in a way, you are essentially solving robot dynamics, right? And this interaction between all the forces and moments with the motion of the robot can be simply written as a function like so in equation 1, where tau is a vector of joint torques, tau1 and tau2, and q dot and q double dot are nothing but the position, velocities, and accelerations of the trajectory, right? So you could simply classify the robot, or you could simply express the dynamic equations of motion using function which maps the joint torques to the trajectory of the robot. Or you could reduce this in a familiar form, which is nothing but the net torque or the net forces acting on all of these joints is mass matrix multiplied by acceleration multiplied by a nonlinear vector. So we call this a vector of Coriolis and centrifugal effects. Vector of Coriolis and centrifugal effects. So now this is actually very familiar. Like even if you take a simple spring, mass, and damper system, it will also have a similar form of equations of motion. For example, if you take a spring mass damper, the equations of motion can be considered as the force is mass times acceleration plus some damping coefficient multiplied by its velocity, plus the spring constant if you have a spring multiplied by the displacement from the free length. So a similar expression, you can also find it for a robotic manipulator, but in this case, it's not one-dimensional, it's multi-dimensional. Like so for if you take a specific case of a 2R robot, the tau vector would be 2 cross 1 vector comprising of tau 1 and tau 2. Mass matrix would be a 2 by 2 cross 2 matrix. Q dot is a vector of the joint variables, the acceleration of joint variables, theta 1 double dot and theta 2 double dot. And N is actually a vector of Coriolis and centrifugal effects. And the derivation of these terms, how to derive each and every single components of this equation, we will see that in the later slides. Okay, so now moving on from this. So just like what we have seen in the case of forward and inverse kinematics problem, we can also have a forward and an inverse dynamics problem. So it's more or less analogous actually. So earlier we have established that forward kinematics is nothing but simulation of a robot, a virtual simulation of a robot. It's similar to simulating the robot in a virtual environment. And whereas inverse kinematics is more similar to controlling the robot. So I hope you can understand why we call the forward kinematics as similar to simulating the robot and why we would call the inverse kinematics as controlling the robot. Because in the case of a forward kinematics, it's basically observing what motion the end effector executes as we give inputs to the joint variables. Right? For example, in the case of a 2R robot, if you give inputs as theta 1 and theta 2 as the joint variables, what would be the coordinates of x and y? So this problem is what we call the forward kinematics, just to see how the robot moves depending on how you change the input. Whereas in the case of inverse kinematics, you would give a desired coordinates, task-based coordinates, x desired and y desired. And if you want your robot to realize this final coordinates, what should be the inputs that you should be giving to the robot joints? So that problem is inverse kinematics. Suppose like if you want to pick an object from x1, y1, and if you want to drop the object onto x2, y2, you need to know the inputs theta 1, theta 2 for the initial position, and you also need to know theta 1, theta 2 for the final position. Then only you would be able to actuate the robot between the initial position and the final position. So such problems, to control a robot from one position to another position or a series of positions, inverse kinematics basically deals with this problem. So you can have a similar analogy for dynamics as well, for where you would also consider the forces that is acting on the robot, the forces being the external forces that is applied onto the robot. There could be inertial forces due to the physical properties of the mass as well as acceleration. There could be the forces that is contributed by the actuators. So all these forces will have some effect on the motion of robotic manipulator. So dynamics is basically finds a relation that maps or that relates the forces onto the motion of the robot manipulator. So similar to forward kinematics, the forward dynamics basically says for a given input vector tau and known joint states q and q dot. So if you supply the joint tau, And if you know the initial states of the robot, the initial position and initial velocity, so the finding the resultant motion of the manipulator is essentially forward dynamics, right? So like from this earlier well-known form, you are already given this vector tau, the input to the joint, and you also know the initial conditions defined by q and q dot. So the only unknown that remains is q double dot. This mass matrix you can estimate from the topology or configuration of the robot. So finding q double dot like so using a simple manipulation of that earlier equation, you can find the acceleration q double dot. And then if you integrate this q double dot, you will get q dot. And further again, if you integrate q dot, you will get q, right? So the new positions due to this forces and the new position from the initial positions due to this effect of these forces will be obtained by this equation and then successive integration of this equation. And then later on, it keeps on getting updated and updated until you stop some value or unless there is some damping on the system. Otherwise, it keeps on going and going and going. So that is about forward dynamics. And in case of inverse dynamics, it says for a given trajectory of vectors, q, q dot, and q double dot, maybe a desired position, desired velocity, and desired acceleration, finding the required input vector tau. That is inverse dynamics. So it's similar to inverse kinematics. It's, inverse dynamics is actually a problem of controlling the robot. It's a way of estimating how much torque you should need to supply onto the motors so that the robot manipulator can track a desired trajectory. And the trajectory would be defined by these vectors, q, q dot, and q double. Okay, so that is about basics of dynamics and what are the specific problems that we would be dealing on robot dynamics. Now, moving on to the derivation of equations of motion of robotic manipulators. So until now, we know the basic structure of equations of motion. It's nothing but the torque vector is mass matrix multiplied by this acceleration plus a vector of centrifugal and Coriolis effects. Now, how to derive this equation for any given robot manipulator? So to derive this equations of motion for any given manipulator, in this course, we follow two methodologies. The first one is called Euler-Lagrange method, and the second one is actually called a Newton-Euler method. So we implement a recursive method. Like Newton-Euler methods can be interpreted in many ways, depending on what frame of reference you chose to define it. But what we do is we make a recursive formulation of Newton-Euler method so that you can easily propagate the forces through the links as well as velocity through from one link to the adjacent link. So we'll start our discussions basically with Euler-Lagrange method. So Euler-Lagrange method basically starts by definition of a scalar quantity called Lagrangian. So that is the starting point of the formulation using Euler-Lagrange. So basically, the Lagrangian, the scalar Lagrangian can be defined as the difference between the kinetic energy and potential energy. So like, for example, a robotic arm can have multiple links, and each of these links can have potential and kinetic energies associated with it. And the Lagrangian of a robot manipulator is simply, it's nothing but the difference between total kinetic energy and the total potential energy. So once you have the Lagrangian, you do this following manipulation as per equation 5 to obtain this equations of motion, right? So the torque vector at each of these coordinates. So this is a vector equation. This is not a scalar equation. This torque is a vector depending on the number of joints that you have. So this torque vector is nothing but dou L by dou Q dot. And we take the derivative of this term, d by dt of dou L by dou Q dot minus dou L by dou Q. So you would essentially get this sort of expression once you do this following manipulation on the Lagrangian. And I suppose we have seen an example of how to write an equation of motion of a robotic manipulator during the live session. We won't be covering that here, but in any case, if you have any doubts, please let us know. And the second method is actually called the Newton-Euler method. So it basically deals with the equations of motion in translation, pure translation. That is what the Newton's equation deals with. So it says the force acting on a rigid body is nothing but the mass times the acceleration of the center of gravity. And Euler equation for a rotating body is nothing but the net torque acting on the body is moment of inertia matrix I alpha plus omega cross I omega. Right? It's actually a sum of two terms. And the Newton's equation basically deals with the propagation of forces, and the Euler's equation basically deals with the propagation of moments. So the reason that we are doing both Newton-Euler and Euler-Lagrange method is that for smaller manipulators like the 2R manipulators, or maybe a few manipulators with fewer degrees of freedom, it would be very easy to formulate this formulate the dynamics equations of motion using Euler-Lagrange. But as the number of degrees of freedom increases, or if the complexity of the manipulator that we are considering increases, then it would be very difficult to derive these equations of motion using the Euler-Lagrange method. The biggest reason is because of the involvement of these partial derivatives. So if you can imagine, if there are multiple terms in this Q vector, taking the partial derivatives of each and every single term, or derivative of this Lagrangian with respect to each and every term of this Q dot vector would be very difficult as the complexity or the size of the robot grows. And another issue of another peculiarity using the Euler-Lagrange method is that you only get the direct torque on the actuators. So to get more clarity, I'll try to bring more clarity into this. So a 2R manipulator, just like what I'm depicting here. So this is link 1, this is link 2. It's well known that this is a planar manipulator. So the coordinates of forces or moments that we need to consider for a planar robot are the forces in X and Y directions and the moment about this Z direction. So this is only a small example. It applies to a manipulator in large scales. And if tau1 is the torque on the first joint and tau2 is the torque on the second joint that we supply onto the robot, this Euler-Lagrange method directly gives you this joint torque. So that is actually good. It's very efficient as long as you only want to estimate these torques. But what about the other components? See, the torque supplied is always along an axis that is along the revolute joints. Right? If this is Z1 and Z2, these torques are always directed along this axis of the revolute joints or axis of the motors. But for a lot of other purposes, maybe for design purposes or for testing the design and its safety, sometimes or plenty of times we may need to estimate the other component of forces. Maybe, for example, if you want to estimate fx1 and fy1, or in this joint. And in this joint, if you want to estimate fx2 and fy2 for any purposes, maybe for example, to design this robot or to select proper materials or to select proper components, we may also need to find out, the other remaining components of the forces or torques. So using this formulation, you won't be able to determine any of this. Or for example, if you want to find the reaction forces between these two links, this formulation will not give you that. It directly gives you the joint torques tau 1 and 2. So that is a serious, like if that is your objective, that could be a drawback of using Euler-Lagrange method. And if you want to use something for design purposes, if you want to find out all the components of the reaction forces, if you want to find the reaction forces and all the other components, then you may have to use this Newton-Euler method. So here it only says the equations of forces and moments as components, right? Maybe this could contain all the components that you are interested in, maybe the reaction forces, all the remaining components of the forces and torques that is not available through Euler-Lagrange. All these things can be taken care of if you are using Newton-Euler. So keeping this in mind, we can actually we can basically propagate the velocities from the base to the end effector, and we can also propagate the payloads from the end effector all the way to the base. So these are the few fundamental equations that we require for a recursive Newton-Euler method. So why do we call this a recursive Newton-Euler method? So there are two schemes to make this Newton-Euler method work. So the first is actually the propagation of forward propagation of velocities and accelerations. So the first one being here, we call this as forward propagation. For example, if you have a robot comprising of n links, so the first link is ground. This would be the first link. This would be the second link. This would be the third link, so on and so forth. And we also have a ground. If we fix this to the ground, attach all the joints to some joints. So if we consider the ground to be fixed, obviously grounds are fixed, then the initial velocities and acceleration for the ground is known to be 0, 0, 0, 0 for any quantities. Maybe omega, angular velocity component could be all 0. Linear velocity components could be all 0. Linear acceleration components could be all 0. Then what else do we have? Linear acceleration also we have, angular acceleration, linear acceleration. All these components of the ground are all 0. Right? And each of these joints will have their own inputs, actually, input velocities. For example, if the first joint is a revolute joint, it will have an angular velocity and an angular acceleration. If the second joint is also revolute, it will also have an angular velocity and angular acceleration. If the third joint is a prismatic, its angular velocity and angular acceleration would be same as that's the previous joint, but it will have a linear velocity and acceleration with respect to this point. So the thing is, we begin from a 0 condition for the ground, and we propagate from ground all the way to the end effector using the forward propagation of velocities and accelerations. Right? So the 0 velocity of the ground is actually compounded by the velocity of the first link, which is then compounded by the velocities of the second link, and so on and so forth. The same case goes for accelerations. So this is how the angular velocity propagates, right? So the angular velocity of I plus 1th link expressed with respect to I plus 1 is nothing but angular velocity of the previous link plus the contribution by the joint input, right? So if you consider omega I plus 1 to be the first link and omega I to be the ground link, this component for the ground link is, this component is basically the contribution by this joint, and I omega I is actually the angular velocity of the ground, which is 0 because it's the initial condition. So velocity of link 1 would be velocity of link 0, that is ground, plus the input velocity that you are giving onto this joint. So it keeps on accumulating as it goes from base all the way to this end effector. And the known initial condition is that the ground is actually fixed. It does not have any initial linear or angular velocities. Same goes for accelerations. So this is how you would propagate angular velocities. And the derivation is actually pretty straightforward. It is actually obtained. It's actually been discussed in the lectures. It is also discussed in the textbook, maybe John Craig's book. I hope this has been mentioned in the syllabus or in the reference textbooks. You can also go back to Professor Shantakumar's lectures to understand how this recursive relations of angular velocities have been derived. And these laws are also available in any standard textbooks on rigid body dynamics. And the same goes for the propagation of angular velocities, right? So this is actually the angular velocity of the I plus 1 link. That is nothing but the sum of angular velocity of the previous joint, plus there is actually this component, I omega I cross the input angular velocity of the current joint plus the input angular acceleration of the current term. Again, this definition is actually obtained by taking the derivative of this expression. If you want to know more about the derivations of these equations, you can actually let me know through the discussion forums. Unfortunately, since we don't have any participants for this session, I don't want to spend much time on deriving or how to obtain these expressions. And yeah, we have covered the angular velocities and accelerations. We also have the forward propagation relations for angular linear accelerations. So the linear acceleration of ith link is linear acceleration of the previous link plus this term, alpha cross pi. Should be familiar with this term. We call this the centrifugal acceleration. Sorry, this is the tangential acceleration, right? Alpha cross r. Tangential acceleration. And this term over here is the centrifugal acceleration. And you can also call this to be, slip acceleration or previous acceleration, anything in the structure. So keep in mind that for rotary joints, these are this equation, right? So rotary joint, in case of rotary joint, angular velocity of current link is angular velocity of the previous link plus the input that you are giving, the input velocity that you are giving onto the robot. So similarly, in case of prismatic joints, you also have the propagation laws. So this is the forward propagation of angular velocity. So notice this is much smaller than the previous case because in case of a prismatic joint, this term does not exist, right? A linear an angular input to the I plus 1 joint does not exist because it's a prismatic joint. It will only have a relative velocity along the linear direction. So in case of a prismatic joint, this term would not be here. So we'll end up with this term only. So angular velocity of the I plus 1th link is angular velocity of the previous link, same. But to make everything to this I plus 1th frame, we also pre-multiply it with this rotation matrix so that it can be recursive, right? So if you know I plus 1, I plus 1 omega I plus 1, you can propagate it to find out I plus 2 omega I plus 2 and so on and so forth. And same goes for the propagation of angular acceleration. So compared to this expression for rotary joint, this term and this term does not exist for a prismatic joint because these are inputs of angular velocity and angular acceleration that you are supplying onto the joints. And because these two terms are zero, we only end up with this term for prismatic joint, which is what is being described by equation 9b. But when you come and take a look at this expression for acceleration, it's much more lengthier than in the case of a revolute joint. Because in addition to the terms that we have covered in revolute joint, there are a couple more terms because due to this existence of this linear velocity and linear acceleration components, because it's a prismatic joint. So similar to this earlier equation, we have this equation that is the tangential acceleration. And over here we have the centripetal acceleration. Yeah, and over here, this is nothing but we call this component 2 omega cross vi dot. It's a product of angular velocity of I plus 1 link and the linear velocity of I plus 1 link. We call this term as Coriolis acceleration. And this term is nothing but the linear velocity of this I plus 1 joint. It's a mistake. It's not theta double dot I plus 1. It's d double dot I plus 1. So maybe you want to call this as relative or slip. Again, to derive these equations for this propagation of accelerations, it's still not a big deal. It can be understood if you follow any textbooks on rigid body dynamics or any of the textbooks are referred as reference textbooks for this course. And yeah, now that we have dealt with the propagation of velocities and accelerations, keep in mind that the propagations of velocities and positions are along a forward direction from the base or from the ground all the way to this end effector. For the Newton-Euler method, we also need to consider the backward propagation of forces and torques. So we have to come the other way, all the way from end effector to the ground, using this backward propagation equations. So again, if I consider this to be a 2-hour robot, I'll label this as ground. This is link 1. This is link 2. These are the joints. So the backward propagation basically deals with the propagation of forces and moments from the tip of the end effector all the way to the ground. And it's fairly straightforward to understand it intuitively because a payload will always have a weight, at the end effector or the gripper. And if you are given a weight of the payload, what will be the weight of what will be the weight at this end of this link 2, right? And once you have obtained the weight at this point, you can then consider, you can also obtain the weight of this point, by solving the equations of motion of this link first and then this link first. So it's pretty straightforward because, for example, if you consider link 2, you have this forces, probably F external. And here, if you consider this reaction forces on link 2 due to the connection with link 1, what are the other forces that are acting on link 2? If the link 2 is stationary, there are no more other forces. But if the link is moving, you also will have this inertial force, right? Mass time acceleration. So the total force acting on this point, can be obtained by taking the sum of this force, inertial force plus external force. So if you solve these equations of motion, you will get the force at this point. So once you get the force at this point, the distal end of link 2, the distal end of link 2, then again you can repeat the same procedure for link 1. Now the the proximal end of link 2 becomes the distal end of link 1. And again, using the free body diagram, if you know F21, and if you also know the inertial forces, F1, then you will be able to obtain the torque or all the forces and torques at this joint. Again, by simply considering the free body diagrams So to proceed with the backward propagation, we need to define a few terms beforehand because these external forces will be given as per this application. Another thing that we need to consider is the inertial forces, actually, the forces due to the arising due to the physical features of the link as well as its motion. So the net force, the inertial force acting on the centroid of ith link is given by mass of its ith link multiplied by the linear acceleration about the center of gravity of the ith link. So that is the forces that is acting at the centroid, center of gravity. And this term ACI, this component ACI is nothing but the acceleration of the center of gravity, and it is nothing but this equation 10b. It's very similar to this equation that we have derived in case of revolute joint, and it consists of this term, a tangential acceleration and a radial acceleration plus the acceleration of the previous joint. Right. So once you obtain this, you substitute this into this, and you can actually have a recursive estimation of all the forces of all the links. And just like we have this here, this Newton equation, we also have this Euler equation. Right. So Euler equation, the moment acting about the center of gravity is I alpha plus omega cross I omega. So now you have obtained the centroidal forces and moments. Now you can actually use the free body diagram of a body under dynamic equilibrium to solve for the forces at the joints. So the force at the I link at the proximal end of that specific link is nothing but the force on the distal end plus this inertial force. Right? It's nothing but, for example, if you have link I, and this side, the proximal side, you have the force vector Fi, and this end you have Fi plus 1. And at the centroid, you have this inertial forces Fi. So the only unknown would be this force because it's a backward propagation. So Fi would be the sum of inertial forces plus the forces at the distal end. And if you bring everything to the ith frame, just to make it recursive, you will have to make use of these rotation matrices, and finally you end up with this expression for the backward propagation of forces. And similarly, you can have a backward propagation of moments. For example, if there is a moment at ni at the proximal end of the link and ni plus 1 as the moment at the distal end, and you also have capital Ni as the inertial torques and moments. So if you take the sum of moments about this point, at the proximal point, so Ni would be sum of the net moment Ni would be due to the contribution of this moment, inertial moment, plus the moment of this one, Ni plus 1, at the distal end of the link. Then the third one would be the contribution of this force, right? The moment as a contribution by Fi plus 1. That is nothing but this Fi plus 1 multiplied by this distance. So if you consider this distance to be Pi plus 1, so the moment contributed by Fi plus 1 would be Pi plus 1 cross Fi plus 1. So the three components, once you bring everything into this ith frame of reference, can be expressed by this equation. So Ni, this moment would be due to this moment, Ni plus 1 plus this inertial moment, Ni plus this distance multiplied by this distance, that is this term, Pi cross Fi plus 1. Then the moment contributed by the inertial forces. This force multiplied by this distance. That is what we have over here, this term. That would be the net moment acting on the proximal end. And using that, you can further propagate it backward all the way until you reach the ground link. And notice that these are actually vectors, not scalars in the case of the Euler-Lagrange method. So as a result, on top of the joint torque, the torque aligning with respect to the same axis, you'll also get the components of forces and torques in all the other directions. So it's basically nothing but the reaction forces which you can make use of while you select the materials or to fabricate the components to see how much stress has been developed. Okay, so with that, we'll solve some sample questions for this tutorial. Yeah. So the first problem is nothing but it's basically it basically deals with the transformation of coordinates from task space to the joint space. So it states that if M of Q is the inertial matrix in joint space and J of Q is the Jacobian matrix, what will be the inertial matrix in the task space? Right? So the thing is, you can write the equations of motion in either of these coordinates. So for example, if you write equations of motion in joint space, it would look something like tau would be M of Q multiplied by Q double dot plus N of Q dot. So I'll write this as equation 1 because we have seen this equation earlier. It's a more familiar form. You can also write these equations of motion like this in joint space. So I'll write it over here, equations of motion, in task space is nothing but instead of the joint torques, we have the end effector forces and moments, F. That would be this mass matrix, M of mu, just to denote that it is with respect to the task space coordinates, mu double dot plus N mu of mu dot, where mu are the task space coordinates. Right? So if you are given the mass matrix and the Jacobian matrix, how would you find the mass matrix in terms of the task space? So I'll move on with the derivation. So from kinematics, so the first expression is actually from robot dynamics. Or you can call this as equations of motion. And from kinematics, which we have seen in the preceding weeks, we can also write as eta dot is nothing but j of q multiplied by q dot. I label this as equation 3, and this is from robot kinematics. Right? So I suppose you are very familiar with this equation, where n dot is the task space velocities, vector of task space velocities. Q dot is the vector of joint space velocities. And j of q is the Jacobian that maps the velocities of task space to the velocities of joint space. So if you take the derivative of equation 3 with respect to time, what will you get? Eta double dot would be j of q multiplied by q double dot plus j of q dot multiplied by q dot. I'll write this as equation 4. And we obtain this by this chain rule. So from equation 4, I can rewrite this expression for q dot because a q double dot term is over here. So from here, I'll write it as eta double dot minus j dot of q dot, the whole multiplied by j of q inverse. This is nothing but q double dot. I'll write this as equation 5. So if I substitute equation 5, that is this term q double dot onto equation 1, what will you get? So 5 in 1. If I do that, I'll get tau as m of q multiplied by, instead of q double dot, I'll write this term. So that will be j of q inverse eta double dot minus j dot of q dot plus n of q dot. And this is equation 6. And from statics that we have seen in the previous week, right, we know that tau is J transpose F. I'll call this as equation 7. And we obtained this from robot statics from the principle of conservation of power. If you have any doubts regarding this, you can refer to the week 4 lectures of Dr. Shantakumar, or you can also go back and visit my week 4 live tutorial session where I think we cover the derivation of this expression. So now writing 7 in equation 6, substituting 7 in 6, we'll get J transpose F as m of q multiplied by j of q inverse have I gotten it wrong? I suppose not. Eta double dot minus j dot of q dot plus n of q dot. So if I bring this Jacobian to the other side of this equality, I have to multiply it with J inverse transpose. So if I pre-multiply this with J inverse transpose, these two terms will get cancelled and becomes an identity matrix. And if I multiply this with J inverse transpose here, you will get the resulting equations as F would be J inverse transpose M of Q, J Q inverse eta double dot minus J inverse transpose M of Q, J of Q inverse J dot of Q, Q dot plus J inverse transpose N of Q, Q dot. So I just make an outline for this. So now we have over here the quantity capital F, that is nothing but the forces and torques at the task space coordinates. And if you compare this equation with respect to this equation, equations of motion in task space coordinates, the mass matrix is nothing but the coefficient matrix of this vector eta double dot, right? Yeah, in here I have used mu instead of eta. Apologies for that, but eta and mu basically denotes variables in task space, right? Or mu, both basically are used to define the variables in task space. So if we compare the coefficient of eta double dot of equation 2 and this equation, the final equation, eta double dot, what can you say about the mass matrix? M of eta is nothing but J inverse transpose M of Q, J of Q inverse. So this is nothing but the mass matrix in task space coordinates. Okay. Let me with matrix. Okay, so I hope that problem has been cleared. So the correct answer for this problem would be the mass matrix in task space is J inverse J inverse transpose M J inverse. So I guess the correct answer in this case would be option A. That is indeed the correct answer. Moving on to the second question. The second question says, in case it's a true or false question, it says, inverse dynamics is the problem of controlling the robot manipulator. So we have seen at the beginning of this lecture the definition of inverse as well as forward dynamics, where we said that forward dynamics is more or less similar to simulating the robot in a virtual environment, whereas inverse dynamics, just like in the case of inverse kinematics, is basically controlling the robot manipulator. That is indeed true. So moving on to question 2, that is indeed correct. Solution. Now moving on to question 3. So the linear acceleration of a prismatic joint as per the propagation equations are. So we know that the propagation equations of prismatic joint is much more lengthier. The acceleration prismatic joint has more number of terms than a revolute joint. So out of this, which of them is the correct option? So we know that the linear acceleration of the previous joint is of the current joint is the linear acceleration of the previous joint plus the tangential component plus the centrifugal component plus the relative acceleration between the two joints because it's a prismatic joint, and then there is also one more term called Coriolis and centrifugal effects. So I strongly suspect that equation A itself is correct because this rotation matrix is correct. In this case, the rotation matrix is not correct because you have to bring everything to the frame of reference I plus 1. So this does that. This does not does that. This also does not do that. So I believe option A is indeed the correct answer. But again, if you want to know how these equations are derived, you can refer the textbook because the preliminary part of this derivation, we have covered it in the previous week. I hope you can recall if you have two frame of references and one frame of reference is fixed, another frame of reference is rotating, translating with respect to frame A. And if you have a vector Q that is attached to frame B, what is the variation of Q with respect to A? And what is the variation of the derivative of Q with respect to A? So from here, actually, we develop the equations for angular velocities and accelerations, as well as linear velocities and linear accelerations. All these equations can be derived by analyzing this fundamental problem. And we have derived a few of those in the previous lectures. And for this current lecture, unless someone makes any specific requests or queries, we don't plan to do that. So the option is indeed, correct answer is indeed option A. And for your live quizzes, you can, get any combinations of these sort of questions. It could be linear acceleration for revolute joint. It could be angular accelerations for revolute joints. All these sort of combinations are possible. So moving on to question 4, it's a numerical problem. I'll read the question first. It says, in a single rotary planar link manipulator, the motor is connected with the rotary joint, is rotating at a uniform speed of 5 radians per second. And the distance between the base frame to the end effector frame is 2 meters. What will be the radial or centripetal acceleration component of this end effector? So I'll simply write down the given data. So we have been given that a rotary manipulator that is rotating at a speed omega as 5 radians per second. So 5k radians per second. I hope you will agree with me using this unit vector k because the rotation of a rotary mechanism would be always along its own axis, right? So that unit vector always remains constant. So omega is given as such, and the distance pi plus 1 with respect to I is given as 2 meters. So I'll write this as vectorially 2I meters, right? And the reason I use this I is because if you recall the DS parameters, we have 4 DS parameters, that is alpha I minus 1, AI minus 1, theta I, and di. And this is called link twist. This is called link length. This is called joint angle. Call this as joint offset or joint distance. And if you know what these are, this is nothing but rotation about xi minus 1. This is translation about xi minus 1. This is rotation about Zi. This is translation about Zi. And we define all the link lengths with respect to x-axis. That is why x-axis of the current frame of that specific loop. That is why I have used this I as here. So now that we have all the information, you are asked to find out the radial or centripetal acceleration. So vectorially, a centripetal is nothing but omega cross by pi plus 1. Right? So I'll take the cross product of this term first. That is nothing but 5k cross 2I. This is nothing but 10j, right? 10j. And we have to cross it again with omega. That is 5k cross 10j. That is 50 I cap. There is also a minus because k cross j is minus I. So you have 50 and 50. Two 50s are there, but one is with minus sign. So that makes this to be the correct answer. Option E for question 4. Okay, so I hope that is clear. Checking the solution, it is indeed option 4. And moving on to question 5. Again, it's a numerical problem. It says, for a given manipulator, the ith angular velocity is given as so. So the angular velocity alpha, sorry, it's omega, right? Omega I is given as 210. And the acceleration vector, it's probably angular acceleration. So alpha I is given as 102. So if the position of I plus 1 joint to the ith joint is given as 120. So position of I plus 1 joint with respect to ith joint is given as 120. Then the tangential acceleration of the I plus 1 joint with respect to ith joints. We are supposed to find out A tangential, which is nothing but alpha I cross IP plus 1. Right? So you have two vectors. How do you take the cross product? We can use the determinants, pretty much straightforward. This is how you do it, ijk. The first vector, you write it as row vector 102. The second vector, you write it as 120. And if you take the determinant, what will you get? That will be I multiplied by minus 4 minus j multiplied by, if you eliminate these two columns, you will get minus 2, I suppose, and multiplied by plus k. If you eliminate these two columns, you will get 2. So this is nothing but minus 4i plus 2j plus 2k. So the correct answer is, if you write it as a vector form, minus 4, 2. And option D is the correct answer. Yeah, that is fine. Moving on to question 6. I think we used the same numericals for the previous question. So in this case, it is asking you the centripetal acceleration. Same thing. So omega I again is given as 210. Then alpha I is given as 102 IPI plus 1 is given as 120. And A centripetal is nothing but omega cross I plus 1p IP I plus. So if you take the cross product of this term first, what will we get? Will be I J K will be 210 and 120. If you take the cross product of this, you will get I multiplied by. So this is 0 minus J multiplied by. Again, this is 0, I suppose. Plus K multiplied by. Suppose it's 4 minus 1, 3. So it's nothing but 3K. So again, if you multiply that with, if you cross product it with this vector, you will get IJK. Omega is 210. Then omega cross K is 3K. So that is nothing but 0, 0, 3. So if you take this, I multiplied by, if you eliminate these rows and columns, it will be 3 minus J multiplied by, will be 6, I suppose. Plus K multiplied by, if you eliminate this and this, that will be 0. So it will be 3I minus 6J plus 0K. So your answer would look something like this: 3 minus 6 and 0. I guess the correct answer is option E. The answer, it is indeed correct answer actually. Now moving on to question 7. Okay, so based on the backward propagation of inward iterations, the joint force model can be given as. Again, this is a fairly straightforward problem. So if you have a joint like this, so like maybe if you want more clarity, I will draw this in 2 different colors. Right. So if this is I plus 1 frame attached to I plus 1 link, you have this ith frame attached to this ith link. So if you know the forces of this I plus 1 link, so Fi plus 1 is known because it's a propagation model. You always know the force that is coming from the other end of it. So Fi plus 1 is known. We also know this inertial forces. Fi, what will be Fi? So if you write the equations of motion, free body diagram, or in free body diagram of dynamic equilibrium, Fi is nothing but Fi, capital Fi, the inertial force, plus Fi plus 1. If you write everything with respect to this ith frame, because these are terms associated with link I, right? This Fi, that is force at this joint, and this inertial force acting through its centroid, these two terms are associated with link I. So they all are respected with respect to ith frame, but this force Fi plus 1 is actually a property of I plus 1 frame that is attached on I plus 1 link. So this will be always with respect to I plus 1. But then you have to bring it everything to this ith frame. You can do so by pre-multiplying it with the rotation matrix. That is I plus 1 with respect to I. Just move it a bit like this. Right? So your IFI would be nothing but the inertial forces. Sorry. Inertial forces IFI plus the rotation matrix I plus 1 multiplied by I plus 1F I plus 1. So in that regard, I guess the correct answer would be, I think option B looks correct. Yes, option B looks correct. So yeah, moving on to our second last question, question 8. We have 9 questions to solve today. Let's see what we have. So for a single rotary link rigid manipulator, as shown in the figure, what will be the torque at the revolute joint? So this is a single link joint. Right? It has a rod of length L with negligible mass, and the whole of the mass is concentrated at the tip at a distance L from this joint. And this is a rotary joint, so it can rotate like this, along the positive x-axis. And the joint variable that it makes with respect to this y-axis is labeled as theta, and its angular velocity is omega. You are asked to find out the joint torque at the revolute joint. Right? So since this is a fairly straightforward, simple mechanism, you can use this Euler-Lagrange method. So I'll write this equations of motion over here as tau is tau L by dou Q dot dou by dou T of dou L by dou Q dot minus dou L by dou Q. You can call this as this Euler-Lagrange equations of motion, where this, I'll label this as equation 1. Right? Where this L, the Lagrangian, is nothing but the difference between kinetic energy and potential energy. I'll label this as equation 2. So what is the potential energy of this link? Right? So potential energy of a mass that is raised at a height is mg multiplied by the height from the diagram, right? This height. So what would that height be? So potential energy is nothing but m multiplied by g multiplied by the height at which it is raised. So that means this height. That is nothing but this L cos theta, right? If this is theta, this height would be L cos theta. So I'll write it over here, L cos theta. Right. Now, what is kinetic energy? Kinetic energy of that point mass, you can consider it to be half m v square. How do you find out this v square? So simply by writing the position coordinates of this point, right, like this, I'll write it over here like this. if this distance is xc, and if this distance over here is yc, you can write this as xc to be L sine theta and yc to be L cos theta. So if you take the derivative of these terms, xc dot is nothing but vc as L cos theta, theta dot. And if you take the derivative of yc dot is nothing but, sorry, this is Vx actually. Velocity along the x component, I'll write it as Vx. Yc dot is Vy, that is minus L sine theta, theta dot. Now, this V square over here can be written as V square is nothing but Vx square plus Vy square, that is nothing but L square cos square theta, theta dot square plus L square sine square theta, theta dot square. So V square is nothing but L square theta dot square. So that makes our kinetic energy to be, I'll replace it. So V square will be L square theta dot square. L square theta dot square. Now, what would the Lagrangian look like? The Lagrangian is nothing but difference between kinetic and potential energy. So L would be half ml square theta dot square minus mgl cos theta. So now we apply this equation 1 onto this Lagrangian. Okay? So the first step would be to find out dou L by dou Q dot, where Q dot is the joint variable. In this instant, our joint variable is theta and theta dot. So I'll replace Q dot by theta dot. So this is nothing but ml square theta dot. Right? Something that is raised to the power, if you take the derivative, it will become 2 theta dot. But there is a 2 over here, so those 2 will get cancelled. So again, so that makes this term dou by dou t of dou L by dou Q dou theta dot. That makes it become ml square theta double dot. Because theta is with respect to time. So if you take the derivative of this term with respect to time, you will get the double derivative of this term. These terms are constant. This is a function of time. So if you take a derivative of this equation, you will get the double derivative of theta double dot. Okay, so now we have solved the first part of this equation. Then what about, I'll put a box over here. Then what about dou L by dou Q? So if you take the partial derivative of this equation with respect to theta, instead of Q, I'll use theta. This term is get cancelled because it does not have any theta term. This term has a theta term. So that makes, and you also have a minus sign here. So that makes it minus mgl. Derivative of cos theta is minus sine theta. Then you also, yeah, that's about it, minus sine theta. There won't be any theta dot because we are taking the partial derivative with respect to theta, not with respect to time. So that makes this mgl sine theta. So now if you substitute this term and this term onto equation 1, that is our equations of motion as per the dynamic Euler-Lagrange principle, you will get the joint torque tau as ml square theta double dot minus mgl sine theta. So in that regard, our correct answer is option A, I suppose. Yes, option A. Moving on to our final question, it's again a true or false question. So the statement says in a serial or a fixed base manipulator, the forces and moment vectors of individual forces are obtained by forward propagation. So we know that in forward propagation, we propagate velocities and accelerations from ground to end effector. And in case of backward propagation, we propagate forces and moments from end effector to ground. So this statement actually means neither. It says forces and moments are obtained through forward propagation. That is obviously false because the only known initial condition of forces would be at the tip of the center effector contributed by the payload. And we using this backward propagation, we will find out all the torques and forces of the subsequent things, that is down the line. So that obviously makes the statement false. Yeah. So checking the answer, that is indeed the correct answer. Yeah, so yeah, I think we have covered all the possible type of questions that you can expect for your tutorial. You can expect different combinations of problems, maybe some different numerical problems, but make sure that you are thorough with the propagation equations of velocities and forces. And you should also be familiar with deriving these equations of motion using Newton-Euler and Euler-Lagrange. We haven't shown any examples in this particular lecture, but in the quizzes, maybe you can expect, a few questions, to find out the torques and forces of any given manipulator. Okay, so with that, I wind up my lecture, uh, wind up my tutorial for this week. So good luck for the weekly quizzes. That's about it. I'm stopping it now. Thank you.